We want to solve the differential equation y prime equals y cubed for y of 0 equals 1. To solve a differential equation in the form of dy dx or y prime equals f of y, notice here the right side is a function of y with an initial condition. Number 1, we write the differential equation using Leibniz notation, meaning in the form of dy dx equals f of y, and then we use the inverse function theorem to write the equation as dx dy equals 1 divided by f of y. Next, we integrate both sides of the equation with respect to y to determine the general solution. Number 4, we use the initial condition to determine the particular solution, and then we should try to solve the equation for y. The given differential equation can be written as dy dx equals y cubed, or if we want y cubed over 1. Using the inverse function theorem, we can write an equivalent differential equation as dx dy equals 1 divided by y cubed. If we wanted to, we could also replace dx dy with x prime of y. Let's also write 1 divided by y cubed as y to the power of negative 3. And now we integrate both sides of the equation with respect to y. The indefinite integral of x prime of y with respect to y is equal to x of y plus a constant. Let's go ahead and write x of y will include the constant on the right. On the right, the indefinite integral of y to the power of negative 3 with respect to y is y to the power of negative 2 divided by negative 2 plus a constant. We'll go ahead and put plus c here, which includes the constant on the right and the left. This gives us x of y is equal to negative 1 divided by 2y squared plus c. This is a general solution expressed as x as a function of y. And now we'll use the initial condition to determine the particular solution. We need to be careful here though. If y of 0 is equal to 1, 0 is the x value and 1 is the y value. We can also say if y of 0 is equal to 1, then x of 1 is equal to 0, where 1 is still the y value and 0 is still the x value. To determine the particular solution, we substitute 0 for x or 0 for x of y and 1 for y, which gives us 0 equals negative 1 divided by 2 times 1 squared plus c. Well, this is just negative 1/2, giving us c equals positive 1/2. So the particular solution, x is a function of y, is x of y is equal to negative 1 divided by 2y squared plus 1/2. But we do want to solve this for y. Let's work on this on the next slide. Let's first replace x of y with x, giving us x equals negative 1 divided by 2y squared plus 1/2. Let's isolate the term with the y squared in it by adding it to both sides, and we'll also subtract x on both sides, which gives us 1 divided by 2y squared equals 1/2 minus x. Let's write minus x as minus x over 1. Let's go ahead and subtract on the left by obtaining a common denominator, which is 2, which gives us 1 divided by 2y squared is equal to 1 minus 2x divided by 2. And now we're going to take the reciprocal of both sides of the equation again, similar to how we change the initial differential equation. If 1 divided by 2y squared is equal to the quantity 1 minus 2x divided by 2, we can say that 2y squared over 1, or 2y squared, is equal to the reciprocal of the right side of the equation, which is 2 divided by the quantity 1 minus 2x. And now let's multiply both sides of the equation by 1/2. Simplifying on the right, 1/2 times 2 is 1, giving us y squared is equal to, on the right, notice the 2 is simplified to 1. We just have 1 divided by the quantity 1 minus 2x. And now to solve for y, we'll take the square root of both sides of the equation. And we do need to include a plus or minus on the right, giving us y is equal to plus or minus the square root of the quotient of 1 and the quantity 1 minus 2x. We're not quite done yet. We know that y of 0 is equal to positive 1. So looking at our solution here, if x is equal to 0, notice how we have plus or minus the square root of 1, but the function value has to be positive 1. and therefore our particular solution is only the principal square root or positive square root. The particular solution to the given differential equation with the initial condition is y, or y of x, is equal to the principal or positive square root of the quotient of 1 and the quantity 1 minus 2x. Let's also verify this graphically. If we graph y equals plus or minus the square root of the quotient of 1 and the quantity 1 minus 2x, we get the black and the blue graph. But again, we were given the initial condition y of 0 is equal to 1, meaning the graph must contain the point 0, 1, which is the black graph, which is given by y equals the square root or positive square root of the quotient of 1 and the quantity 1 minus 2x. So this graph does verify our solution is correct. I hope you found this helpful.